Hi everybody, today we're going to start section 0.4, which is involving systems of equations. We're going to spend 3 days on this section, splitting it into different ways of solving, and then we are also going to apply them to real-world situations. This first day, we are going to solve systems of two linear equations using substitution. Before we get to that, let's review what a system of equations is in general. All it is two or more related equations. Now, so there could be two equations, there could be three, there could be seven, but the number of equations is always equal to the number of variables in the equations. So these two examples we have down here, we have a system of two equations to begin with. And as you see in those equations, there are only two variables, x and y. This one doesn't have to have a y in it. As long as one of them has a y, we are good. Now in the system of three equations, there are three variables. As you see, we have x, y, and z showing up here. That ensures that we can solve for each variable. You can only solve for an equation for a system if the number of equations is equal to the number of variables you see. Lucky for us, we are starting with just systems of two, so we're going to be seeing equations similar to that. Okay, we can solve systems in different ways. Algebraically is basically, pen and pencil doing operations, doing algebra. There's two ways we do that. We do substitution, which we're doing today. Tomorrow we'll be doing elimination. A great way to also solve is graphically. Graphically works a lot easier with a graphing calculator because it makes sure that it's 100% accurate. But what we do when we solve graphically is we graph all the equations and we find the points where they intersect. So the solutions, anytime we find them, are actually ordered pairs for our purposes today. But if we were solving this system of three equations, it would be an ordered triple, x, y, z. But we're sticking to this today. Okay, so let's get to solving a system of two linear equations using substitution. Your learning target is I can solve systems of two linear equations using substitution. Our instructions say solve each equation using substitution, express each solution as an ordered pair, x, y. That's very important because remember, these solutions represent the point where the two graphs intersect. If we look at example A, and remember what substitution is. We used substitution to check some of our equations a couple days ago. We were just plugging in a value for a variable. Well, in this case, we're going to be plugging in expressions in a variable to cancel out that variable. And with substitution, we want an equation that is solved for a single variable. So if I look at this second equation right here, y equals negative 2x plus 2, it's already solved for y. So this would be perfect to choose. We take this negative 2x plus 2. Because it's equal to y, I can take that and substitute it in for y in the other equation. Now, just like if I were to have a substitute teacher, that teacher would take the place of me. So this expression takes the place of that y, which means my equation now only has one variable in it, x, and I can solve. First, going to distribute that negative sign. So I have x plus 2x minus 2. Combine like terms, 3x minus 2 equals 7. And continue to solve. Add 2 each side and divide by 3. So we have x equals 3. So we have half of our solution. Remember, our solution should be an ordered pair x, y. This is the easy part. Now that we know x, we can simply take that x value and substitute it in that y equals equation and find what y equals. So that would be y equals negative 2 times 3 plus 2. Oh, I wanted that to be blue. There we go. And so negative 2 times 3 is negative 6, plus 2 is negative 4. So our answer is the ordered pair 3, negative 4, and what that represents is the point where those two graphs would intersect. Looking at letter B, we have 18x minus 7y equals negative 24, and 9x plus y equals 15. Now, neither of these are solved for a single variable, so we find the easiest one to rewrite, and that looks like it would be the second one, because if you notice, this y is by itself, kind of. We need to get rid of the 9x. So if we just move that 9x over by subtracting it on both sides, I have the new equation y equals negative 9x plus 15, and I am not going to use that original one anymore. I can plug this expression in for y in the first equation, which will leave me with 18x minus 7 times this expression, negative 9x plus 15, equals negative 24. And here I just continue to simplify and solve. I will distribute this negative 7. Now, negative 7 times a negative 9 is a positive 63x. Negative 7 times 15, I used my calculator. I got negative 105. That equals negative 24. When I add 18x plus 63x, that gives me 81x minus 105 equals negative 24. I'm going to add 105. Again, you can use your calculator for all this. I just am doing that you cannot see. And what I get there is 81. Well, if 81x equals 81, I divide by 81 and x equals 1. Now I know what x is, and I can plug that into my equation that says y equals in for x. So y equals negative 9 times 1 plus 15. So that is negative 9 plus 15, which is equivalent to saying 15 minus 9, and that is 6. X equals 1, y equals 6. Your solution is the point 1, 6.